Welcome to Optical Communication course. So today we learn a link power budget. So in the link power budget, so what will be the loss in the point-to-point communication or point-to-point link in an optical fiber? So that we need to know before understanding the link power budget. So in the link power budget, we need to know about that what will be the minimum received power level received at the receiver. So in this we need to know that what will be the optical power received at the photodetector so that we can find out what will be the total loss occurred in the point to point link in a optical fiber communication. So that's why we need here what are the various component in a optical link that will provide a loss to your link so that your received power level will be reduced. So we see here a optical power loss model for a point to point link. So now if you see that in a point to point link we have the optical source, a optical source here, and that will emit a light, and then we have some a fiber fly lead that is connected to your source. Okay, now this is a part of optical transmitter, we say, or your transmitter section, and then nearby to the fiber fly lead. So this one we say that a fiber fly lead. Then we have the at this transmitter we have the a connector. This is nothing but a connector here, and then your fiber will move towards the receiver there. That is about your optical fiber here, and then in between that fiber length we have the splices. We're supposed to be consider that these are nothing but the splices of your optical fiber here, and then that is about your optical fiber. Then we're supposed to be use again, because in between that we require a connector. If we have any repeater or anything else, then we require a connector in between this link here. Okay, so then your optical fiber, then we have the for this given length of the fiber there is a splice, then there will be a connector, and at the end we have the optical receiver. So this one is your light comes from this optical fiber, then it will be fall on the detector. This is called as a photo detector. This particular portion we say here a fly lead. This one is about a optical receiver. This one we say that is about we have this a connector here. Here we have again the same connector. You can say that a connector here. Then it will in between that we say that these are the splice. This one we can say again a splice. These are the two splice. Okay, so that is just like a splices here. So you can say that that will be used to. There may be multiple splices like that. Okay, that's why you can say that about it. In between the line or a length of the fiber, there will be splices. There are the many connectors between the line that will be used, and then this portion is about your optical power loss model for the point to point link. Now, if you see here in this overall diagram here, so this one is about a transmitter part. For the source, there is a fly lead, fiber file fly lead. Now that is about a transmitter block, and then here to connect a fiber, we require a connector. So then there may be a losses occur at this connector, that is the LC. Then we have the fiber splices because that length of the fiber is a large. So then we can say that a splice loss. We need to use a join the two fibers. So that's why splicing using a splicing technique. We can join the two fiber. So that's why the losses due to the splices, losses due to the connector, losses due to the splices, losses due to the connector in this optical fiber length. For the given length of the fiber, what will be the total length of the fiber? What will be the minimum power received at this receiver there? So here we need to say in terms of a link power budget, what will be the minimum power received at that particular length? So here link means that is about your total link. So here we need to know about for a given particular length of the fiber or link. So what will be the minimum power received? So that minimum power received is depending upon that what are the various losses occurs in this particular link. So that's why a power received at this detector that is depend upon that amount of light that will be launched through the source inside the fiber, that is either LED or laser, and then there are the losses inside this a fiber link, and that losses due to the connector or losses due to the splices. So we should know that what will be the total losses in a given particular link. So we need to obtain that what are the total loss based on this various number of elements. So that's why we can say that a loss inside this given optical fiber is nothing but what a 10 log of P out by P in. Now we can say that what will be the P out and P in. P out and P in is nothing but what a power entering inside the optical fiber. Here we can say that a P in, and here we can obtain that what will be the P out at the detector. Okay, across the detector, not here. Okay, across the detector. So what will be the power received at the detector there? So power entering inside the optical fiber and leaving the optical fiber. That's what we can say that is about a power loss. And that loss are depend upon the various components. That components are a connector, splices, or somewhere if we use a repeater. So according to that, there may be a losses because of that components present in the link there. So in the link power budget, so what will be the contribution of the loss component for a given particular link? So we should calculate that particular loss for a given particular link. And then for the given particular loss because of the contribution of all these elements, along with that we need to consider some link power margin, and that link power margin is provided because we have few components, that is connectors, slices, or whichever the components we are connecting here, and that components are degraded because of that aging, because of that temperature fluctuations, and because of any other problem occurs on those particular components. So that because of that there may be losses, and that loss is nothing but the marginal loss or a system margin loss for a given particular system. So means for a given particular link, the total power loss that will be depend upon that it losses of all these components as well as some system losses. So if you consider that a total power loss, in the case of a total power loss, that is about a loss between that a source to a receiver there. Losses between the transmitter and a receiver there. And in between the transmitter and receiver, we say there is connector, there is splice, there may be losses due to the length of the fiber. You can say that a fiber attenuation loss. And again, we say that there may be some system loss. And again, there may be losses if we connect improper fiber. So there may be a losses there. So that's why, just like we say, it is about a losses due to the a fiber there. So we calculate here a total loss that will be a power entering, or what will be the power entering inside the optical fiber through this fiber lead here from the light source, okay, inside the fiber, means power coupled inside the optical fiber, and what will be the power received at this receiver there. So we should know that what will be the receiver sensitivity in terms of a power. So we'll get that here we have used a two connector at the end we supposed to be considered. So we say that a transmitter loss, transmitter and receiver, there may be a connector. So if this connector is there in between the link, that can be optional one. Okay, that can be optional connector. Plus, we have the loss due to the length of the fiber, and then we can say that a system margin. And that will be the total loss for a given link. Then a receiver sensitivity, we say that receiver sensitivity, it is depending upon that what will be the bit rate. Means we can say that it is depending upon that what will be the BER. Because we use a generally format return to 0 and non-return to 0. So in that case, that pulse width we say for the given particular on and off pulse. If one pulse width, that is on pulse width, suppose it is about a TB duration, then that receiver sensitivity will be depending upon that what will be the particular pulse width there. So based on the format, that sensitivity changes or that rate will be changes. For return to zero and non-return to zero, there may be a difference of the half of the bit rate here. And then that will be the format we are using while transmitting the signal from the transmitter side. So we have a given particular source and we are transmitting the some power there. So now for the given link, we say that sensitivity part, along with that we need to know that what will be the losses for the given length of the fiber. That is here we have a connector loss, this will be a constant, but this loss factor, it is depending upon that length of the fiber. And system margin is about depending upon that what will be the receive sensitivity and what are the other components there. So for the overall link power budget, so we talk about that for a given particular link length. Okay, this is about length, whatever the link we have for the given particular length of the fiber here. Okay, this will tell you what will be the length of the fiber. For the given particular length of the fiber, what will be the total attenuation? So here we use a word that is the link power budget, but in another sentence, if you see that it is nothing but a power budget for the given length. So means we say that we have, for example, we say that for a 10 kilometer of a length, so we require that value of a power. For 15 kilometer of a length, uh, link length, so we require a y value of a power. So means power level is depending upon that what will be the length of the fiber. If that length increases, then other parameters again increases, and that other parameters means what? Attenuation is depending upon that length of the fiber. The signal distortion, again a dispersion and other factors are there, and that will be depending upon that length of fiber. So even if we say that it is about the power, but we say that a link power budget, it is depending upon that length, because at the receiver we are receiving some particular power. Here at the receiver receiving some particular power, it is depending upon that length. For x length of the fiber, what will be the minimum received power that will be received? That is about in terms of a link power budget. So another part we should know that is about a rise time budget. In the case of a rise time budget, for a given optical fiber link, what approach we are using? Means we say that here we have transmitting some particular pulse that will be representing the bit information, and we are receiving that particular pulse at the receiver. So if you see that data rate, transmission data rate is a higher, and if you compare at the receiver, it is a smaller here. Means at the transmission side, the bandwidth will be large, and the receiver has a narrow bandwidth. Because when we transmitting a simple pulse, that pulse get degrade because of the dispersion. So now here in the terms of a rise time budget, that rise time is nothing but what? What will be the pulse rise time? Okay, that is what will be the pulse rise time. that is a 10 to 90% of your input pulse. Similarly, at the receiver, that is about a 10 to 90%. So that is about a rise time budget. So that is about a total rise time budget of the link is equal to the root sum square of the rise time from each contributor to the pulse time degradation. Now a total system rise time, it is equal to a sum of a rise time contributor, we say ATI here, I is equal to 1 to n bracket raised to 1 by 2. That is about a root sum square of the rise time from the each contributor to this pulse time degradation there. Now in this case here, so what are the contributor for your pulses there? So now in that case, we should know that what will be the rise time of the transmitter. Then that is, we say that TTX, that will be the a transmitter rise time. Then we can talk about that a group velocity dispersion GVD, that is group velocity dispersion time, group velocity dispersion rise time, transmitter rise time, group velocity dispersion a rise time. Then we have a T model here. So we can say that a modal dispersion rise time, and then at the receiver we are receiving, that's why receiver rise time. That is about a contributor. What will be the rise time contributor? So now if you see that here, this two factor that is related to the dispersion. So we can say that even we can write here instead of that T dispersion. So it can be a velocity group velocity dispersion, or we can say that it's about a modal dispersion. So we can write either a two separate term or we can write only a single term, that will be sufficient for the rise time budget. So what will be the rise time budget? Because we have seen that a eye diagram, and in that eye diagram we say that for the given particular width of the eye, that power is to be detected with respect to that what will be the level and all. So at the receiver, what will be the total width, so that we are able to detect that whatever the pulse we are transmitting. So in case of a transition time degradation, okay, if we consider that a digital link, and in that digital link we say that 10 to 90% here of a rise time we supposed to be consider. So that in that case, a transition time degradation of a digital link, if we use a non-return to zero format, so then that transit time degradation, that should not exceed that a 70% of a non-return to zero bit period. And in the case of a return to zero, So it will be of a 35% of a transition time degradation for the return to zero. So we consider that a 1 bit period, it is nothing but whatever the duration of a pulse we say a TB, that is about a 1 bit period is giving you the what will be the data rate. So that is about a format for the your inputs. From the input side we can say that what will be the data rate, and according to that we can find out that what will be the minimum rise time required for those data rate there. But in the case of a transmitter and receiver side, so we supposed to be consider that we are providing that input from this transmitter side, that is about a source. So means a transmitter rise time, it is primarily depending upon that what type of a light source we are supposed to be used, or what combination. We say that for a bit there is a information, means for 1 it is on, for 0 bit there is off, likewise so on off. So similarly at the receiver side, so we are receiving the signal, means from the light source side we say that a driving circuit will be responsible for a transmitter rise time, but at the receiver side, the receiver side, that receiver rise time, it is depending upon that what will be the photodetector response for the given light. Means light falls on the photodetector, then a response of a photodetector, and it is again depending upon that what will be the driving circuit for this receiver side. So means at this end, at the receiver, how many number of photons falls on the detector, and then that will provide you the information about the bit and all. And then that length of the fiber, because of that length of the fiber, pulse get degrade. So that's why there will be a dispersion there. Okay, there will be a dispersion. So if you consider that in the both the case, here is we have a pulse duration. So we transmit some particular signal that is about on off. Similarly, we are receiving that particular on off light. So means at the receiver, your rise time is depending upon that a detector response, and what will be the bandwidth at the front end of the receiver. So means we can say that a 3 dB electrical bandwidth of the receiver. So generally we say that a 10 to 90% of a rise time, and if you consider that a receiver bandwidth is about a B here, so in that case a TRX is equal to what? It is about a, depending upon that 350 by a B here. Okay. So means we supposed to say that that receiver bandwidth, it is about a receiver bandwidth here. So your receiver rise time is depending upon that a 3 dB electrical bandwidth at the front end side. Then that is about a receiver rise time. So similarly, we need to find out that what will be the transmitter rise time, because the pulse we supposed to be transmitting, that is a rise time is directly we can obtain input side it is fixed, but at the receiver side it is depending upon that what will be the receiver bandwidth. Then again another factor here that will be contributing the rise time budget of your fiber optic link. So that is about a fiber rise time, group velocity dispersion here, and that a group velocity dispersion rise time, it is depending upon that what will be the spectral width of the optical fiber. So means spectral, not optical fiber, spectral width of the optical source. So we can obtain that a rise time t, group velocity dispersion rise time, it is depending upon that spectral width of the source and the dispersion. So that is about a sigma lambda. Now if you see that here, that sigma lambda is nothing but that a spectral width of source, L is the length, this T is nothing but it is about a dispersion. T is nothing but the dispersion. And the dispersion is depending upon that what will be the length of the fiber. Okay, that dispersion is depending upon that what will be the length of the fiber. So we can calculate that what will be the total dispersion for the optical link. And then another factor is about a dispersion, that is about a modal dispersion. So in the modal dispersion, we need to know about that what will be the modal rise time. Okay, to obtain that this T modal, that is what we can say that a modal dispersion rise time. So in this T model here, we should know that what will be the modal rise time. And that modal rise time, it is depending upon, or that modal rise time will give you the bandwidth, and that bandwidth for this modal rise time. So we obtain here, so what will be the fiber we are using and what will be the modal rise time for the given particular fiber, and based on that we can find out the what will be the bandwidth for this particular fiber there. So modal dispersion occur, and that because of that modal dispersion occur, so we will get that the bandwidth because of that modal dispersion, that is about a Bm, and that can be expressed in terms of B0 here, and that is a B0, it is nothing but a bandwidth of a 1 kilometer length of the fiber, L raised to Q here. That generally that Q is ranges from zero point 0.5 to 1. So if we consider that a Q is equal to a zero point 0.5, if Q is equal to zero point 0.5, that indicates that a steady state modal equilibrium. Okay. And then if we say that q is equal to 1, then that indicates that a little mode mixing. Okay. So generally that q value is to be considered a zero point 0.7, so that we'll get that a modal bandwidth there. And from this modal bandwidth, we can write what will the pulse broadening occur for a given particular length. So we can calculate that a pulse broadening occur for this given particular modal distribution. So if you write here in the range of that a total fiber length is nothing but what Tm of n, that is about the n section of the fiber, that is about the length of the fiber, and that is nothing but Tmn is nothing but what a pulse broadening. We say a pulse broadening is equal to a sum of a Tn raised to 1 by q, n is equal to 1 to capital N raised to q. That is about the n is nothing but what will be the total cable section for this given length of the fiber. Means Tn is about the a length of the fiber, or we can find out a Bm based on the a curve fitting of this particular dispersion there. You can say that sum of n is equal to 1 to n 1 by Bn raised to 1 by q. So we obtain that what will be the pulse width and what will be the pulse broadening for this given particular dispersion. So in that case, for a given particular fiber, we should have to calculate that what will be the 3 dB bandwidth, optical 3 dB bandwidth, and that optical 3 dB bandwidth, that will give us the what will be the a modulation dispersion for the given particular modulation of a frequency there. If we have that particular modulation of frequency, then we will get that a particular modulation frequency, and that is depending upon that what will be the RMS pulse width. So we can calculate that a T modal dispersion, that is 0.44 by Bm is equal to 0.44 L raised to Q by P0 here. Okay. So if we consider that a T modal dispersion, if it is in a nanosecond, T mod in a nanosecond is equal to 440 by Bm is equal to 440 L raised to Q by P0. For this AT model dispersion here, so we supposed to be consider that a by Bm it is in a megahertz. So we'll get that particular equation there. So total system rise time is equal to what? We said that earlier, a total system rise time, that is about a transmitter rise time square plus 440 L raised to Q by V0, that is rise time for this model here, plus D square sigma square L square plus 350 by BE square raised to 1 by 2. Now this is about a transmitter side. If you see that this expression here, this one is about a transmitter side. This is about a modal dispersion. This is about group velocity dispersion rise time, and this is about a receiver side dispersion. And if you see that the all the time expressed here, it is in terms of what, a nanosecond, and this a sigma, this one is about a sigma lambda, okay, and that sigma lambda is about the spectral width of the source, and that d is the dispersion, that is to be expressed in terms of a nanosecond per nanometer into kilometer, and we have this electrical bandwidth we are supposed to be consider, that is in terms of a megahertz. So from this expression, if you see that here the rise time budget, total system rise time budget, this transmitter rise time, that is about a pulse here, and this one is about the electrical bandwidth, because that length of the fiber changes, that bandwidth changes. So that's why at a front side of the receiver, what will be the total bandwidth? And then here the dispersion is again depending upon the length. This dispersion, modal dispersion, is again depending upon that length. Means even if we obtain that rise time budget of a optical link, it is totally depending upon that a length of the fiber. So while designing the optical fiber link, we should know that for a given length of the fiber, so what will be the minimum power received or required at the receiver, and what will be the total rise time budget for the given length of the fiber. So if you consider that a length required for the power budget and length required for this system time, so if you compare both the thing, so power requirement can be a minimum, but rise time, okay, if you consider that particular rise time, that will not be acceptable for the given particular length of the fiber. So in this particular length of the fiber, what will be the minimum power acceptable by this fiber link? So that is about a link power budget. Similarly, what will be the minimum timing, system time, total system rise time required for this given optical link? So that will tell you a total power length of the optical fiber there. Okay, so that is about your link power budget of your optical fiber link. We have seen that a link power budget for this optical link, and we have seen a rise time budget for the optical fiber link. And this all this link power budget and a rise time budget, it is totally depending upon that what will be the length of the given particular fiber. With this, we conclude that a link power budget, we say that what will be the minimum acceptable power required for the given length of the fiber, and what will be the minimum rise time required for the given bit rate or a given bit error rate. So that is about we have seen today, that is link power budget and a rise time budget.